All right, so as promised, we'll take a look at 4 different ways that we can implement the determining of the size, 4 different strategies. They will all inherit from this base abstract class, where they inherit all the methods except this one method that they're all going to implement themselves, right? And then we'll compare and benchmark their performance. First, we'll implement the naive strategy, the one that we know it's not going to perform. And we'll do it by, we know that underneath Java, when it's concatenating, it's always ever only asking for an additional character, right? So that it can add this additional character, and by throwing away and having to reinstantiate a brand new one that is only one character bigger and copies over the next character. So we'll implement that first. We know it's not going to be any better. We'll call it the ExactArrayStringAccumulator. So we'll instantiate only the exact amount that we need, right, and no more than that, right? So we're going to be very conservative on the size of that array, as conservative as we can. We know it's going to have the same poor performance, right? Basically, when the ensure method asks that I need to be at least one more character as big, right? The determine NewCapacity is just going to return to you exactly how much you asked for, right? So if I have 10 characters and my already filled up in an array of 10 characters, and I need to concatenate an additional character, meaning I'm going to have to be of size at least 11, right? It's going to come back to me here and says, well, yeah, that's exactly how much you need. You need 11. And so resize is going to look at the 2 comparisons and says, well, how big do I have? It's 10, and how much do I need? 11. I need to resize. Right? It's going to throw away the old array. It's going to instantiate the size of 11, right? And then it's going to have enough space to add the new character. Yes? And that's exactly what string does when it concatenates, right? It throws away, adds a new character, and that's what creates the low performance. Right? So this strategy is the worst you can do. Right? It's just return exactly what you asked for. One more character, that's all I give you. So this is not any better. How about we go a little further, right? And perhaps the amount that we ask is as opposed to just asking for 1, right? Perhaps the amount of size that we can ask perhaps grows linearly, as the size of the array grows, right? So the bigger the array grows, the more aggressive I get. Right, the more it grows, the more aggressive I get. So it'll be some multiple or some ratio, of the speed at which I'm growing, right? So that looks like a more aggressive approach, right? So it'll be some multiple or some ratio of the size that I already have, right? So we can decide how aggressive we want to be, right? So the multiple that we want to grow by, right? Maybe it'll be 10 times as big as we already have, or 20 times as much as we already have, right? And it'll be a ratio that we maintain as we grow the array. So in this implementation, we arbitrarily choose that we want to grow 16 times the size that we already have. So if we run out of space, right, we'll grow 16 times bigger, right? We'll say. A ratio of that size, right? It will be some ratio of the current size and that step. So it's a ratio of the current size, 10 over 16 or whatever that is. Okay, and we can choose different steps. And what we'll notice here is that this certainly will be better, right? We'll see in the curve. Right, we'll see that it looks almost linear, right? But then when you zoom in, right, we'll see that it actually has the same shape. Right, it actually has the same shape. So this will be definitely much better than the default implementation, but for large enough strings, it's still quadratic, right? Definitely it grows less often, right? Definitely it's but when you do the quadratic summation over time, you still come back to have the same exact summation, n times n plus 1. But the constant is so much smaller, right, than the constant that you would get in the default implementation, just because you are doing it so many fewer times than the default case, right? So, but it's still quadratic. It's still quadratic, but the constant is so much smaller. So we need to try and improve even further. We need to grow less often still, right? We need to minimize even further the amount of times that we ask for a brand new array, and we have to copy everything over. So a third option might be that, go even further, even more aggressive. I'm going to grow twice as big as what I have, right? So if I ran out with 10 characters, well, now I'm going to ask for 20, right? If I ran out with 20, I'm going to ask for 40, right? If I run out of 40, I'm going to ask for 80. So the more I run out, the more space I grow faster and possible, right? So in this case, we're asking for twice as much as we currently have, and so we'll later on we have when we graph this out in the in the benchmark, we'll realize that the size that we're growing is fast enough, right, to catch up with the filling up of the characters, right, to be able to compensate with the amount of times that we need to throw away the array and copy them over, right? So this is our first successful attempt at bringing down the quadratic. Is going to bring it down to almost linear, right? So this is our first. We'll see in the benchmarks that this is our first success at bringing the bringing down that performance curve down to linear. Or finally, go as big as you can, right? Go as as much as the system might give you. Give me the largest array so that I won't ever have to grow, right? Just give me the largest array that you can possibly afford, right? So that at most I would ever have to do this once. Allocate the array only once and then never again. Now the current implementation that we have doesn't allow us to choose the array size on the fly, right? It is hard coded as a constant, right? It's the current array. We have I think it's constant that says the size of the array, the default size of the array. Although we could perhaps approximate this behavior using the following. We'll see the implementation in a minute. Now the problem that we risk, obviously, is that we indeed ask for something that is so huge, right? For a string that is so massive, right? That we are actually going to run out of memory. Right, so there are some edge cases that perhaps we need to guard against. That there might be some, within some reasonable limits, we will be able to perform very successfully. Right, obviously within some reasonable limits. There's always a risk of these edge cases that we need to consider. But other than that, right, in normal cases, we would have the best case scenario where we exactly allocate the array only once and never again. Right? We don't hit that overhead of having to copy things over or anything like that, right? So this is choosing perhaps some outrageously big number, or some we're using 100,000 here, or you could use some big integer or some number that we know. It's going to be the limit of some size of some array or some integer. So we're now ideally the base case scenario is that the size that you need, right? That the size of the array that you need, the resulting array, is going to be 10,000 characters, and so you allocate exactly what you need, as opposed to allocating every so often. Yes. That the resulting character is 60,000 characters. Well, that's exactly what I'm going to instantiate, and then I just add one character where they go. That's the ideal, right? But we don't have that, right? The problem that we're trying to solve is to do it one character at a time, right? So this is not a realistic solution. In practice, being able to a priori be able to know how big do we want? I mean, that's the whole point why we invented concatenation in the first place, right? That we do one character at a time. So even though this is the best case scenario, it's not very realistic, right? That we would know something a priori that we need 100,000 characters to allocate. Yeah. So let's take a look at how these performs against each other.